Hello and welcome. In this video I'll discuss NMR spectroscopy, probably the most powerful and versatile of the routine molecular spectroscopies, although also the most expensive. Just like the previous two spectroscopies I've dealt with, by the end of this video and the associated classes, you should be able to describe how NMR spectroscopy works in terms of the instrumentation and the molecular properties involved. And you should be able to use NMR spectroscopy, particularly in combination with IR, to determine structures of molecules. Parts of chapters 10 and 12 of Chemistry Cubed are your best bet here. Be particularly careful online, as NMR is easy to get wrong and there's a lot of dodgy information out there. The phenomenon of NMR is much more complex than UV visible absorption or the excitation of vibrational modes using IR, and deals with the magnetic moments of nuclei. If you consider nuclear magnetic moments, then generally they have no particular orientation, and furthermore they change their orientation very easily. However, if you apply an external magnetic field, then they behave as if they become aligned either with or against it. This is an oversimplification, but it'll do for now. If you now apply radio waves of the correct frequency, then you can alter their orientation and study their behaviour as they return to the equilibrium situation over here. This can tell us an incredible amount about our sample. The NMR spectrometer is also much more complex and more expensive to both buy and run than the UV vis or IR spectrometers. There are three main parts to it. Most of the bulk of the spectrometer is just a big thermos flask with a magnet hidden in the middle of it. Here's the magnet itself, a superconducting solenoid which is immersed in liquid helium, which is itself kept cool using liquid nitrogen. This magnet gives a very strong and almost perfectly homogeneous magnetic field. Up the middle of the magnet is the probe. This contains the radio frequency coils, which act as both transmitters and receivers, contains tuning capacitors, which set the frequency of the RF coils and therefore select which nucleus you're observing, hydrogen, carbon or whatever, and then these little shim coils to increase the homogeneity of the magnetic field, making it exactly the same over the entire of the sample. The sample is lowered into the probe right in the centre of the magnet. Then there's this console over here which communicates between the computer and the probe and controls pretty much everything. In terms of the acquisition of spectra, again it's more complex than UV or IR. Nuclear magnetic moments respond rather slowly to the magnetic field, so we don't sweep the frequency range one wavelength at a time like we do in UV vis, because we'd have to wait several seconds at each frequency before moving on to the next one. It would take a really long time to acquire the spectrum that way. Instead, we just have one waiting period, and then we use a short pulse of radio frequency radiation. This excites a wide range of frequencies of nuclear magnetic moment, allowing us typically to acquire the entire spectrum from one pulse. We then observe the free induction decay, the decay of the signal back to equilibrium, for the entire sample at once. By repeating this a few times and adding the FIDs together, we can improve the signal-to-noise ratio and therefore the sensitivity of the spectrum. The most important thing, though, to note is this. You are measuring resonance of the magnetic moments as they return to equilibrium following the pulse. You are not measuring absorbance or emission of radiation. So, what do we actually learn? Well, NMR is very information dense, and unlike the other spectroscopies we've met, every peak can and should be taken into account. This makes NMR very powerful, but it can also make it tricky to get your head around. The first thing to do, though, is just count the peaks, or the resonances as they're more properly known. This tells you how many nuclear environments there are. A nuclear environment is a unique position within a molecule. So, there are 3 nuclear environments for this molecule for both hydrogen and carbon. This is one, this is another, and this is the third. These 2 hydrogens, for example, are the same as one another, as they are an equal distance from all other parts of the molecule and they're related to one another by symmetry, so they form one environment containing two hydrogens rather than forming separate environments. If two or more groups can be interconverted by symmetry, by bond rotation, or by some other exchange process, then they will be in the same environment as one another. In this case, the number of hydrogen and carbon environments are the same, but they can be different. For example, if you have carbons with no hydrogens attached, or if you have alcohols or amines which have hydrogens that are not attached to carbon. The next thing to look at, then, is the x-axis, the chemical shift. This expresses the frequency of the nuclear magnetic moments as a part per million difference to the applied frequency. Essentially, though, different chemical shifts tell you about the different types of nuclear environments present. In their simplest form, and certainly for the lower half of the spectrum, where all the peaks are in this case, they tell you the proximity to an electron withdrawing group. Higher chemical shift means closer to an electron withdrawing group, or that the electron withdrawing group is stronger. The nitro group here is a very strong electron withdrawer, so these two protons and their carbon will have the highest chemical shift. These two protons and their carbon will have the next highest, and these will be the lowest. So why do we get different chemical shifts? Frequency is proportional to the magnetic field strength, but if the applied magnetic field is constant, how is it different for different nuclei? The answer to this lies in the electron clouds that surround the nuclei. When the sample is placed in the magnetic field, these electrons start to circulate, generating a magnetic field of their own. At the nucleus, this opposes the applied magnetic field, giving an effective magnetic field that is different to the applied one. If you then include the cumulative effect of all the other induced magnetic fields from the electrons surrounding the neighbouring atoms, then you find that the effective magnetic field at a particular nucleus is very sensitive to the local molecular structure. A tiny change in structure may have a significant effect on the effective field. These, then, are the simplified chemical shift scales for hydrogen and carbon. Aliphatic groups, so simple hydrocarbons, have low chemical shift, and the chemical shifts increase if electron withdrawing groups are nearby. Alkenes and aromatic groups show up in the middle third of the hydrogen spectrum, or the third quarter of the carbon spectrum, and the top end is where you'll find carbonyl groups. Okay, back to the spectrum. The next thing to look at is the integration, the relative area under each resonance. This tells you the relative number of nuclei in each environment. So, you'll find that this peak and this peak have the same area as one another, whereas this one has an area 50% higher, as that environment contains 3 hydrogens, whereas these two contain 2 each. The important thing here is that it's not the height of the resonances that's important, it is the area. So this short broad peak has the same area as this tall skinny one, because they arise from the same number of hydrogens. For carbon, however, integration is not reliable, so you just don't need to worry about it. Finally, we come to the most powerful piece of information from NMR, the splitting of the resonances. This tells us about the number of nuclei neighbouring those causing the resonance. This in turn allows us in many cases to piece together the entire structure of a molecule. This resonance, for example, is split into 3 lines, a triplet. This tells us that the hydrogens causing this resonance are next to 2 other hydrogens, no more and no less. So this group must be next to this group. This resonance is also a triplet, so the hydrogens causing it must also be next to that group. They can't be next to this one because we know that this one is definitely not split by the 3 hydrogens of this group. The resonance in the middle, then, is split into a sextet, split into 6 lines, because the hydrogens causing it are next to all 5 of these hydrogens in red. This may be confusing at first, but it's very, very useful, so hang in there. Carbon, however, again, typically doesn't give splitting information, so for carbon spectra we only have to consider number and position of the resonances. This is simpler, but obviously less informative. The formula for splitting is given here, where n is the number of neighbouring atoms causing the splitting, and I is the spin quantum number, which helpfully is half for hydrogen and lots of our other favourite nuclei, so the formula simplifies to n+1 for hydrogen and these others. So, if there are no neighbours, then a resonance is a singlet, 1 neighbour causes a doublet, 3 neighbours causes a triplet, and so on up to the rare and crazy cases where you have 9 neighbours causing a resonance to split into a decade. The ratio of the intensity of the lines is given by Pascal's triangle, where you keep adding the 2 adjacent numbers together to give the result in the next row. So, for example, in the triplet, the central line has twice the area of the 2 outside lines. Finally, I'd like to consider the effect of magnetic field strength. Here's the spectrum I showed you before. It was acquired using a 2.1 Tesla magnet, which gives a resonant frequency of 90 MHz for hydrogen. If we acquire the same spectrum on the same sample in a 7 Tesla magnet, which gives a resonant frequency of 300 MHz for hydrogen, then this is what we see. The peaks are taller, you can't tell very well here as both spectra are so good, but the noise level in the baseline is much lower in this spectrum, allowing us in principle to use smaller amounts of sample to get equivalent results. This means that the instrument is more sensitive. The peaks are also narrower, and you can clearly see that the splitting is tighter. This is still a triplet here, but you'd need to zoom in to see it. And this means that the resolution is better. It's easier to distinguish between 2 resonances with similar chemical shifts, and there are fewer overlaps. Overall then, bigger, powerful and more expensive magnets give better spectra. Okay, so we're done with NMR. As with the previous videos on UV and IR spectroscopy, I've talked a bit about the underlying principles of NMR, the spectrometer itself, and how differences in molecular structure give rise to NMR spectra, although really I've just scratched the surface with all of these, and there's a great deal of complexity hidden behind it all. The main use of NMR, as I showed you, is for determining structures of molecules by considering the number of resonances, their chemical shifts, their integrations, and their splitting patterns. Sometimes you may want to use IR or other techniques to resolve any ambiguities in the spectrum, but often a combination of hydrogen and carbon NMR will be enough to solve the structure of a small organic molecule. NMR also has lots of other uses that I haven't considered here, but that's a story for another year.